Okay, you should get 9-2 out before you try this out. And so if you don't have that, go ahead and get 9-2 out. We're just going to do the very topmost little bit as part of our notes. And I'm sorry about the notes-a-thon, but that's kind of what this day is. We're trying to get through a lot of material that, frankly, we should do it a different way, but, you know, you have an AP test, and so I must obey. I'm going to talk about something called the marvelous Millikin oil drop experiment. I did this in college. I can tell you for a fact. I am firmly tongue-in-cheek when I say the marvelous Millikin oil drop experiment. It is an incredibly painful experiment to do. So if you get a chance to do it, don't. What the experiment involves is two metal plates, metal plate, and in this metal plate at the top we punch a hole. We attach these things to a battery. And when we attach it to a battery, we also attach it to something that allows us to control the flow of charge. More on that later. We also, by the way, use something called an atomizer, which sounds really cool. What an atomizer is, and probably you guys have never seen these before, there is a bottle with fluid in it. In the old days, we put perfume in it. Nowadays, you attach this to the end of a hose, and then you have something that you can squish so you can shoot air through here. And as the air brushes past here, it pulls out globules of fluid which float through the air. And at the good old days, you could get yourself perfumed by squishing the little air pocket. It would blow this particles of perfume, and you'd run around in it, and you'd be perfumed. Well, if you do this near a metal plate, there is some non-zero chance, and I will say it's sometimes it doesn't happen, or maybe often doesn't happen. One of these little droplets will float through the metal plate. Isn't that nice? Now, as part of this arrangement, you also need to have a beta particle emitter. So you have a little pin through this, which is a beta particle emitter. What a beta particle emitter is something that shoots electrons. It's radioactive, but it basically shoots electrons. And so it's shooting electrons at random. Occasionally, this little dot of oil is hit by an electron. And when that happens, the thing becomes charged. Now, if I have the battery at the bottom is charging, the bottom plate is negative, and the top plate is positive, and you can adjust the amount of charges on these two. As this thing floats downwards, you can actually trap it. And if you trap it, you can then go, aha, force of weight of the drop. Now, it's a microscopic drop, so you're using a microscope shooting through the side of this to look at your drop floating in the air. And use a little density over here and some fancy stuff to get what its mass is. But we don't care because that's not important. KQQ over D squared. Now, I'm controlling where the plates are. I'm controlling the charge on the plates. Okay. The universal constant is not changing, so what do I have left over? I got the charge of whatever the oil drop is. And that charge of the oil drop does something fascinating. If you do it and you wait a while, you might get 3.2 times 10 to the negative 19th coulombs. You might get 4.8 times 10 to the negative 19th coulombs. You might get 1.6 times 10 to the negative 19th coulombs. You might get 6.4, am I doing that right? Yeah, 6.4 times 10 to the 19th coulombs. But you will never, ever, ever get a number between these values. Never. What? Never. You're never going to get a charge that is somewhere between these values. So the smallest one you'll ever get is this one. And so it came to Milliken's observation that, in fact, what's happening here is this is a charge of 1 electron. And you can't have 1.5 electrons or 1/3 electrons. You can only have, say, 2 electrons stuck to your blob, or 3 electrons stuck to your blob, or 4 electrons stuck to your blob. But you can't have anything in between because there's no such thing as 1.5 electrons. And so he came up to the conclusion you cannot split these apart. It can't be done. And so the charge of the fundamental particle of an atom that carries charge is negative 1.6. So do charge of an electron, 1.6 times 10 to the negative 19th coulombs. And so that is our fundamental charge. And by the way, in spite of this experiment being a pain in the neck, it actually gets you the right answer. So who am I to argue with them? By the way, if the charge of an electron is 1.6 and a single proton cancels it out, what's the charge of a proton? Waiting patiently. Nobody's answering me today. What the heck? You guys are real quiet today. Negative 19th coulombs, which brings up a point. Make sure you ask questions, send me notes, whatever. I will try my best to do whatever I can to communicate with you in whatever fashion. And if it gets really bad, we'll figure out some sort of crazy thing like Uber meetings software or something done like that. But for right now, we'll do this. Okay, so that's our charge. Does that make sense? Okay, now, that said, there's not a really great way to ask the question, is charge breakable? But AP Central has asked it on almost every test, even though it's not even listed on their things they're actually testing you for. So let's get a sample problem and figure out how would they ask you such a ridiculous question. And so right below this is your question. Go ahead and look at that question, try it out, and then we're going to talk about that question right now. So go ahead and do that. Pause this if you still need more time. You should need more time, so pause it. I'm talking to you. Pause it. All right. So here is an experiment theoretically done. The experiment says, all right, we've measured the charge caused of, we have a charge, we don't know what it is. We put it next to a charge we know. The charge we know is in the bottom. We see how much force it is by putting a spring scale attaching to it. Somehow they can measure this small bit of force. And so the question is, well, they ask the question, they say, 1, you can determine the charge of the second particle. 2, you could, I don't know what it is, the answer C, you could, find the electric field, which we've never talked about, so don't answer that way. And then D was, hey, this experiment's bogus, and I would not trust it for anything because it's giving me charges that don't make sense. Huh? Look at the chart. Down here in this realm right here, they have data points for, say, 0.5. They have data points for, say, 0.5 times 10 to the negative 19th coulombs. You can't have that, can you? Yet they're showing data, the charge they're putting in is 0.5 times 10 to the negative 19th coulomb. You could have 1.6 times 10 to the negative 19th. You could have 3.2 times 10 to the negative 19th. You could have negative forms of those things, but you can't have 0.5 times 10 to the 19th. So this experiment is bogus, and therefore you would not trust this experimenter to determine any of the values that it thus far claims could be done. Does that make sense? So again, how they test this is how they test it. What you really need to know for my class is that the charge is this, and you can't get fractions of this, right? You can get a positive. This is the negative form, which is the charge of an electron. This is the charge of a proton, and no, you can't ever get 1 times 10 to the negative 19th because you can't make a fraction of it. Now, some people later on go, wait a second, you said there's a 1.3 coulomb charge. Yeah, okay, so that's a whole cajillion of electrons, because it would take times 10 to the 19th electrons to make this charge. And yes, you could find that down to where it'd be the 16th, 19th decimal place you'd have a difference. You can't tell at this level whether or not this is a rational charge. It is down in that 9 times 10 to the 19th area that you can tell whether you have a bogus charge or not. So don't over panic, don't overthink this. And I'll frankly tell you, they pretty much tell you this is going on by the way the question's phrased, because most of the questions will be like, this doesn't make sense. What are they talking about here? Does that make sense? Okay, so that's where we're at. This is the last video for today. I am sorry about all the talkage, but your instructions are on Teams. But basically, I want you to do assignment 9-5 now, and that will be the end of it for Monday. Again, questions, please post things in Teams. Please post things as inside of by sending me emails, and I will do my best to send out answers of whatever form. If I have to make videos, whatever, I will happily do so. All right. Thank you very much, and I will pause this now.